So yeah, hi. I'm Alvaro. You already know me from that great introduction. And at UC Santa Cruz, my research and my teaching is principally focused on distributed systems, right, which is the reason we're all here. This talk is called The Twilight of the Experts. It's sort of my own really personal hot take on the state of the art in resiliency for giant scale systems. Why I think that at present and in the foreseeable future, the state of the art is kind of fucked, actually. And some of my thoughts on how we might be able to unfuck it with the help of nascent observability infrastructure, right? The other reason that we're all here. So by way of introduction, we are extremely cool kids. And because we're cool kids, we program and deploy and operate distributed systems at massive scale, right? In fact, every non-trivial system that I can think of that I interact with nowadays is a distributed system. And because we understand distributed systems, we know they're friggin' hard to program and doubly hard to reason about. And well, what do I mean by distributed, first of all? All I mean by distributed is that our systems require the cooperation of some number of independent physical machines, right? And these systems are hard to reason about because of a failure mode, I'm gonna argue, mostly because of a failure mode known as partial failure. Is that a term that's familiar to people, partial failure? Right, so like, if a single site fails, like my laptop fails or my phone fails, typically I detect that failure and I replace the component or I reboot the component or something like that. But in a distributed system, of course, some subset of those communicating entities may fail to uphold their function, but the computation may nevertheless finish and produce an outcome. And so every time a distributed system gives us an outcome, we kind of have to go, is this the right outcome? Is it correct? Is it complete, despite the fact that partial failures may have occurred? Now, because partial failures do occur, all distributed software ever written has been written to be fault tolerant, right? What do I mean by fault tolerant? Well, I just mean it's got software in it that makes an attempt to anticipate, detect, and then ultimately mask or mitigate those partial failures so that they don't affect our computational outcomes. The question we should be asking ourselves, though, is my fault tolerant code actually going to tolerate faults that occur in practice? Have I tested it exhaustively? You haven't. So in the first third of this talk, I want to go over some of the sort of cultural myths and legends and bedtime stories that we've told ourselves so that we could sleep at night, knowing that our shallowly tested code is running far away from us in production, right? And maybe the oldest and the most comforting of these bedtime stories is the myth of the experts, right? Like, can't someone else do it? Like, how many fault tolerance challenges are there? Can't we just sort of delegate responsibility for solving these really hard problems to, the greatest minds of our time? Can't we let the Lampsons and the Liskovs, the Grays and the Lamports and the Chandis sort of solve fault tolerance and then encapsulate those solutions in reusable components, libraries? And then mere mortals like us, right, could just build stacks on those libraries. This isn't so unreasonable of a thing to hope for, right? This is kind of how we have classically conquered complexity in traditional computer systems, at least single-site systems, right? So there's a genius, this guy, who's an expert in something that I'm not an expert in, and he works on a problem and solves it, and then he realizes that his solution isn't necessarily interesting or important to the users of it, right? He can obscure that solution and provide an API, and then we can go build stacks on top, right? We can take unreliable components and have a genius turn them into the illusion of a reliable component, and now we can compose. This has worked in the past, right? It worked for redundant arrays of inexpensive disks, right? There's a happy-go-lucky end user who believes that they're interacting with logical volumes that just don't fail, damn it. Now, of course, underneath the covers, disks fail. Disks partially fail. But those failures can be completely masked because a controller can detect the loss of a volume and then, migrate over from a mirror, all the while preserving this transparent illusion of disks that just go down. So this guy can build a stack of pancakes, and we can keep moving up. Right? This is what keeps us from having to be experts in the bits and bytes, in the signals, right? This works great. Wait, does it? Well, this worked great on single systems that didn't suffer from legitimate partial failure, right? This worked because the RAID controller, a hardware component, well, it could have been a software component, but a hardware component in this case, was able to be a perfect failure detector, right? It knows the difference between a disk that is no longer spinning and a disk that's just slow. Because if you get that wrong, you're going to have serious problems, right? The difficulty is that in a distributed system, there's no such thing as a perfect failure detector. I'm going to say that again. In a distributed system, there's no such thing as a perfect failure detector. This is fundamental. If there's one thing you remember from this talk, remember that. There's no difference to me if a computer on the other side of the world crashes, it's never coming back, than if that computer on the other side of the world just went into a lengthy GC pause. Right? Failure is just the absence of a message in a distributed system, which means we can't hide the complexity. We can't turn this substrate into a reliable component and build up. Our abstractions are going to leak. Well, heck, they're going to do more than leak. They're going to burn down. The way that like NFS burned down by trying to pretend that that disk that was on some other computer that might be up or down, pretend it was mounted on your disk, that was fucked. That didn't work. RPC that, I do an RPC and I don't know whether it succeeded or failed, that's fucked. That's a leaky abstraction. In distributed systems, fault tolerance goes all the way up the stack. Okay? Okay. So much for that myth. But it's okay, because I don't want to rely on experts to build things I don't understand anyway, right? So if we can't rely on experts, the sort of second myth that's now in its sunset is the myth of formally verified distributed systems. Well, if we can't have experts build them, maybe mere mortals like me could build them, and I could have some really good tools to like check my work. And that's how a model checker works. It takes my program that some idiot like me wrote, and it just enumerates all the states that the program could ever be in, and checks them all against my invariants. It says, all of the states are good. This program can never get into a bad state, so you're cool. It turns out, and I'll go quick through this, that this isn't going to work for the same reason that the experts didn't work, because of this sort of elusiveness of compositionality for fault tolerance, right? Model checkers, for example, do not scale well to large state spaces. They work great on hardware, not that well on software, and really terrible on distributed and concurrent software. You couldn't, for example, model check Netflix. There's too many states. The sun will be burnt out before you check them all. So the best hope would be what's called modular verification. Verify the pieces, the services, and then make sure that your guarantees compose as you compose the services. But as I sort of already indicated, this doesn't seem to work. So we're not going to be able to have experts do the hard stuff. We're not going to be able to try to solve the hard stuff ourselves and have a tool check it. And so in industry, as well as academia, in the last 10 years, with some notable exceptions, there's been a race from like the left side of the spectrum, exhaustive but intractable approaches to software quality, to the right, sort of incremental pay-as-you-go but kind of unprincipled approaches based on extending the best practices in testing, integration testing, with fault injection. And this goes by a number of names, which I'll talk about in a moment, but I kind of want to ignore those distinctions and think about them all as one big group. We have moved from understanding a system in some formal way to like running a system and doing stuff and seeing what happens. And I think that's not as bad as it sounds, because it represents a fundamental shift that we were going to have to make sooner or later. So here's this computational artifact that is very complex. And let's imagine this computational artifact getting bigger and bigger. You've got your site, you're adding new functionality, you're making your software more robust. A complex artifact only gets bigger, right? And at some point, it will be too big, even for a super genius, even for a Lamport, even for a Liskov, to hold it in their head. It will be too difficult for a model checker to enumerate all the states. In the limit, as our systems scale, they're going to become black boxes. Maybe you're not at that inflection point yet, but you will be. And if what you've got is a black box, you're going to have to give up on any approach to making it work right that involves understanding what goes on inside it. The experts understood what went on inside it. The model checker understood what went on inside it. The tester does not. The tester does understand the inputs and outputs to the black box, though. So we begin to build hypotheses about what a black box is doing based on the behaviors it exhibits as it transduces inputs into outputs. You give it some inputs, you see what outputs it produces. You give it some inputs and inject some failures or delay, and you see what outputs it produces. You're sort of walking around the black box and formulating a hypothesis about its behavior, like what it does rather than what it is. And I'm going to argue this is the future, because in the limit, everything's a black box. I think that's neat. But we can't all go home, because you can't just combine integration testing with fault injection. There's too many faults that you would have to inject, right? It's a combinatorial space. So when I was at Netflix a couple years ago, we were studying this application that involved about 100 communicating services, pretty large number. Now, if we wanted to combine integration and fault testing in some exhaustive way, we would say, okay, what we'll do is we'll run an integration test for every possible combination of faults. right? So if we were only looking at one fault, that's fine because 100 executions, that's like 90 minutes. Let's say an integration test takes like a minute. Okay, hour and a half to run all your tests. But if you wanted to be a little ambitious and say, well, what if we wanted to see if the service stood up if combinations of up to 4 services were crashed? That's actually 3 million executions. That's like 6 years or something. If we wanted to go up to 7, that's 16 billion executions. That's over 1 million years of running integration tests. And if we wanted to test them all, that's like a 1 with 30 zeros after it. That's heat death of the universe time, just to test this one application out of dozens at Netflix. So we're going to have to be smart about how we select our experiments if we're going to do this testing plus fault injection thing. Everybody with me? OK. One way to search a space is to flip coins. And the early chaos people did exactly this, right? This is how Chaos Monkey works. We're going to kind of throw darts into this combinatorial space of faults. And if there's lots of bugs, it's going to work, right? You're like, oh, I threw 5 darts, I found 2 bugs. Chaos testing is awesome. But I don't need to try very hard to convince you that this thing isn't going to turn black anytime soon with like 1,000 little stabs, right? So the people did that for a while, and they're doing it less. And really, the emerging state of the art now is what I might call going back to the geniuses. Let's hire a super genius who can understand the totality of the interactions across our site and formulate hypotheses about what combinations of faults are most likely to cause trouble for a particular application, right? We need to exploit domain knowledge about the services to know what the dark corners are. So that's cool. So there's a whole field, and then they take a genius-guided walk through this space. That's awesome. So 2 giants have emerged in this space. And I'm going to argue right now that they're exactly the same. What I've written down are the differences. But, chaos engineering, as exemplified by Nora Jones over here on the left, Netflix, and Jepsen testing, as exemplified by Kyle Kingsbury over here on the right, are the same. They involve principal observation of a distributed system followed by targeted fault injection, where the super user has formulated a hypothesis about what set out of that giant space of faults is the most likely to drive the system to a bad place. Now, there are some distinctions, right? The target applications are different, the scale is different, the challenges with respect to availability of source code are different, and of course, the gold standard of what it means to be correct is a little different. But if you ignore those minor distinctions, Nora and Kyle are in the same game, and they're the world leaders in this right now. Problem is, there's only one Nora, and there's only one Kyle. And I don't think that a technical solution that involves a mostly closed loop with a super genius in the middle of it really makes any sense at all. These are people who you have to tell a company you're going to have to acquire and retain somebody who is much better than anybody else, somebody who the process that they're carrying out, we don't know how it works. We don't know how to characterize it. Okay, so in the remainder of this talk, I'm going to prove by example that we don't need super users like my friends. We can automate them out of a job. But here's the trick. We can automate them by observing them in precisely the same way that I argued they observe the systems under test. Okay, so we can turn the magnifying glass that they put on the systems on them, and we can figure out how to get them out of a job. Like I said, there's genius, but I can't see inside his soul. I don't know how he transforms observability into fault injection schedules. So I got to treat him as a black box, right? But a black box whose inputs and outputs I know, that I can walk around and try to infer what is the function that this genius implements. Well, okay, so what does Kyle do? How does Kyle do what he does? Read his blog, he'll tell you. First thing he does is he reads the docs. He needs to read the docs because he needs to figure out what guarantees the database thinks it makes and how it might fail to uphold those guarantees in practice. And then, then magic happens, I don't know. He makes some opaque, brilliant mental model that I can't understand that allows him to target good faults that drive that system into a bad space very quickly. Okay, he observes, he thinks, he acts. How does Nora do what she does? Well, it's the same picture, except she works at a microservice-based organization. Of course, they don't have docs, or the docs aren't up to date, but you can get around that by a little legwork. She talks to service teams, asks about the API, kind of infers what would have been in the docs had they taken the time to write them. And then, magic happens. She has some mental model that I have no reason to think looks anything like Kyle's mental model, right? Some opaque mental model. And then she chooses faults that break Netflix, and then they fix it, and then they increase their availability, and everybody's happy. And so there's a genius in the loop who we want to get rid of. Well, bear with me here. First, let's take the genius out of the loop. Let's say, what can we say about the genius besides that he's a genius? Well, We've already said, well, these geniuses have some kind of mental model of the system that's different from system to system, that tells them what are the bad faults for that system. Okay. So will you accept that there is a mental model in there? Okay, good. I figured I would get away with that. But I think we can do better than that. If it's a mental model that tells us what faults to inject based on what we've observed, both when the system's in steady state and when it's being perturbed by faults, then surely it's a mental model of the fault tolerance of the system. Why do I say that? Well, because remember, there's this big space of faults, and there's regions of it that we don't want to search. In fact, we only want to search a very narrow set of regions. Why would I not inject a particular combination of faults? Well, because I know that the system will tolerate it, right? So anything that tells me what faults I don't need to inject is telling me that because it has some, I don't know, it knows how the system works around faults. Must be. With me? That was a little bit more of a stretch. Everybody still with me? Okay. We can go one step further. Because if it's a model of fault tolerance, it's surely a model of the system's redundancy. Why do I say that? Well, I say that because fault tolerance and redundancy are the same thing, right? Sure they are. Sure they are. A system is fault tolerant if it provides more ways to get to a good place, then we anticipate there will be obstacles, right? Now, this redundancy might be played out in a variety of dimensions. It might be played out in the dimension of space in the form of timeout and retry, or in the dimension of in the dimension of time in the form of timeout and retry, in the dimension of space in the form of data replication, representational dimensions in the form of error-correcting codes and write-ahead logs. But if anybody thinks they know of a fault tolerance mechanism that doesn't involve redundancy, punch me in the face. No, but tell me about it over beer. Okay, so it is a model of system redundancy that tells them, built from observations, that tells them what faults they should do by telling them what faults they don't need to do. Okay? Here's the punchline. We can build models of redundancy based on tracing. I have a proof by existence prototype that we developed in my lab called Lineage-driven fault injection that I'm going to, how much time do I have left? Well, I'll see what I can do. So I'm going to talk about that for a minute, not go too deep. So it's based on the idea of lineage, explanations provided by a system about a particular computational outcome. The richer the explanation, the better, but it turns out that Dapper-style call graphs are good enough, okay? So we begin with some successful computational outcome. Here's an example. I did a write to some distributed storage system, and that write was stable. It was durable. That was good. I'm happy. So I asked my tracing system, why did that good thing happen? And maybe I get an explanation like this. Well, it's stable because it's stored on a replica. Well, that's good. Well, but it's also stable because it's stored on another replica. So my explanation of why the good thing happened has included evidence of the system's redundancy in it. Okay, but why was it stored on replica A, we recursively ask? Well, because replica A received a broadcast. But maybe that broadcast timed out and happened twice. So there's two reasons why it's on two replicas. Everybody with me? And now we bottom out. It started with the action from the client. So this is what's called a lineage graph or a provenance graph, a very coarse-grained one. So now, trying to devise faults, the game becomes, can I come up with a set of faults that represent cuts in this graph that like break the flow from root to leaf? So for example, here is a point in that combinatorial space. Crash replica A and interrupt broadcast 1 with a network partition. We can see that this is not an interesting fault, right? Because there's a way to get to the good place, right? By contrast, this looks promising. This appears to break flow. We should probably experiment by injecting that fault. Okay, now how do we turn that from something that a human has, sort of human graphical intuition into something that's efficient for a computer to perform? It turns out it's pretty easy. So we're going to mine out the individual paths or trees that are sufficient to establish the good thing. Like if the client just did one broadcast and it just got to one replica, the write would be stable. And then we're going to write down over here what faults it would take to make it not so. Well, to break that path, you could crash replica A or interrupt broadcast 1. But wait, there's another way to get to the good place, to the happy place. We write down how you break it. Another way, break it. Another way, break it. And when we're done, we've consed up a formula in conjunctive normal form we can just pass to a SAT solver. The solutions to this satisfiability problem are going to be the interesting cuts. For example, the solver might say, hey, try this. Now, we still need to use our fault injection infrastructure to do it, because this system hasn't necessarily revealed all its tricks yet. We might go inject those faults, and the system says, ha-ha, I can time out and broadcast again. Well, that's fine, Because now we get a new trace that we use to enrich our model, make smarter suggestions in the future. So the property that we get is that, first of all, we're not just casting darts randomly into this space. We're casting them at the cunning regions. But more importantly, when we cast the dart, it casts a shadow over a region of the search space we don't need to search anymore. This very quickly converges to either finding a bug or telling you, hey, I ran out of moves. Okay? So, I have snapped in place of a very expensive and irreplaceable super user, just a thing, just a bunch of code. And the key enabling technology to all this is that finally, I've been waiting for years, observability infrastructure is starting to come of age. Okay? Where does observability come in, you might ask, in a pipeline like this? Well, God, everywhere you look, right? Like, first of all, when we run the experiment, we need to know whether it highlighted a bug or revealed another way that the system works around a particular fault. They're both valuable, right? If we found a bug, we go fix it. If we didn't find a bug, we enrich our model and make a smarter suggestion. So we need observability right there. Did the integration test even work? And sometimes work is not a binary thing, as we all know. But then even more importantly than that, let's say it did work, and we have new evidence of fault tolerance. We want as rich of a possible explanation, not of what people are typically using observability infrastructure for, what went wrong, but just the opposite. What exactly went right? When I injected a set of faults that I hypothesized would bring the system to its knees, and the system nevertheless worked around it. Right? That's the key piece of information. Let the observability infrastructure tell me what went right. Okay, so it's far-fetched, totally far-fetched, I know. But it actually, it works. It's had successes finding bugs sort of across the stack in low-level protocols, commit protocols and consensus protocols and broadcast protocols and things like this, to large-scale applications. We found 11 critical user-facing bugs at Netflix, and it's even found some success in finding funding from the federal government, which, it's not easy to do that anymore. So that's great. So I think I'm out of time. And in case you fell asleep, there's 3 things I want to leave you with. The first is that if it were possible and easy to sort of compose guarantees as we compose functionality in distributed applications, distributed systems wouldn't be so hard to program and administer. But we don't seem to have a way to do that yet, right? We build these building blocks, but as we snap together the blocks, the assurances don't snap together with them. I feel like this is the grand challenge facing distributed systems research over the next 5 or 10 years. But unfortunately, I have no idea how to solve it. So if you have any ideas, please talk to me. The other thing I want to leave you with is if somebody comes to you and says, I have a technical solution that I want you to deploy at your company that involves acquiring and retaining a super genius, run like hell. Or better than that, let them come on board for a little bit, watch what they do, and automate them out of a job. Okay, I've got my PhD student, a former master's student, and a former undergrad in the house. If you want to ask us about how we do this and what we're doing at eBay this summer with this stuff, trying to apply some of these approaches to stateful interactions where somebody's trace from a week ago could have an effect on my trace now and things like this, please come talk to us. And thanks to everybody who gives me money. Thanks, everybody.